in astronomy only. So here with you, don't give up. Okay, thank you very much, Sancho Panza.
I think it's the spice. The other way.
Okay, so okay, during these 50 minutes, I will try to talk about the work we are doing here for the last 2 years, more or less, on the magnetic constraints of the habitability of extrasolar potentially habitable environments. Okay, this is a work that has been done by a group of collaborators here in Medellin, but also the University of Texas and the New Mexico University in the US. And okay, no, the light former, this is a former postdoc at the Lyme Institute postdoc, but today is inhabitant of Canada. Most of this work has been already published, but there are a lot of things that I will try to share with you today that is work on progress. We have already put this summary of these ideas, all this theoretical work in some journals, some papers during these 2 years. Okay, so let's start with a few very basic ideas about habitability and its relationship with magnetic fields. The first thing we need to take into account is that there are two conditions for habitability. You know, habitability is this idea that some places in the universe can have conditions to harbor some life in the surface. Okay, actually, it's very important to stress that we are talking about surface habitability, because there is the possibility that life could also thrive inside planetary bodies, like in the moon Europa, in the Jovian system. So we are talking here about surface habitability. The first basic condition for habitability is the well-known condition, is the condition of insolation. Insolation is the amount of light that a planet receives from its host star. Insolation defines what we call the radiative habitable zone, which is the critical distance to the star, where the amount of light is enough to have surface temperatures compatible with the existence of liquid water. But there is a second and very, very important condition that everyone forgets normally, or think that is granted always, and it's the existence of a dense and wet atmosphere. If you don't have a dense atmosphere, you can forget about having liquid water on the surface. So the problem is that this condition is not only granted inside the habitable zone, but this condition is not always granted. And the physical constraint or the physical condition you need to have this are much more complex than this. The solar system has taught us several lessons about habitability and its relationship with magnetic fields. For example, as you for sure know, Venus, Earth, and Mars are actually inside the habitable zone of the sun, the habitable zone of the sun. So actually, these three planets are habitable from the insolation point of view. Okay, of course, the habitable zone has very different definition. So in some definition, Venus is out, Mars is out, and even in some definition, Earth is out. So we use an optimistic definition of the habitable zone. The three of them are habitable. But as you know for sure, only Earth is actually inhabited. Only Earth has habitability conditions on the surface, because you can see. So, what happens in the solar system if we have three habitable planets why just one of them is actually inhabited. Well, the key factor seems to be the magnetic environment of these bodies. These two bodies, okay, for example, Venus and the Earth are very similar among them. But Venus doesn't have a global magnetic field produced or generated from the inside. And Mars is very different than the Earth, but in any case, it's more cold than the Earth, so it has the condition to preserve an atmosphere. But anyway, Mars is not inhabited today, and it's because it also lacks a present global magnetic field. So, the question is, using this lesson from the solar system, what could we expect for extrasolar planets? We are studying right now the condition to have habitability constrained by the magnetic fields in Earth-like exoplanets. We will call it exo-Earths, around single and binary stars, but also around moons of giant extrasolar planets, aka exomoons. So I will try to give you a very rough view of what we have learned during these couple of years about habitability constrained by magnetic fields. Okay, so what do we need to understand if an extrasolar planet, which is actually located inside the habitable zone, is actually habitable? The first thing we need to know as theoretical astronomers, because actually we don't have yet any observation about this. This is theoretical. We only have the solar system. The first thing we need is a model of the interior. So that's why Paolo, me, and our students are working very hard here to understand the physics of planetary interiors. We are assuming that most of the terrestrial planets in the universe produce a global magnetic field, a global intrinsic magnetic field, due to the so-called dynamo effect in a liquid iron core. This effect is acting in the core of Mercury, the Moon, have acted in the past at Mars, at the Earth, at Ganymede. So we assume that this is a very universal mechanism. Of course, you can expect that also other mechanisms could create magnetic fields in this kind of planets, but this is the main mechanism. Actually, as you know also, the interior of a terrestrial planet is made by two phases of iron, one liquid and one solid. And this is very important because, for example, in the Earth, most of the energy feeding the magnetic field of the Earth doesn't come from the heat stored in the core, but from the latent, not from the sensible heat, but from the latent heat released during the solidification of iron. This is a very important point. Okay, so we have developed well-constrained and well-proved models of the interior of the planets from 0.1 Earth masses to 10 Earth masses. It's assumed that terrestrial planets, it means planets made by silicates and iron, are more or less in that range of masses. We don't know still if we could find a terrestrial planet, a planet made by of silicates of 100 Earth masses. What the model of planetary formation said is that if you have such a large planet, this planet will start to accrete gases and become probably an ice giant. So the masses of our planets are just until 10 planetary masses. Okay, I need to add that Pablo next week will talk about this particular, about super Earth more in depth. I will try to jump right to the most, I think, exotic things we are studying right now. The other thing we should have right now in order to understand this thing is how the thermal energy inside this planet evolves. Since the energy for the dynamo comes from the release of latent heat in the solid core, and of course from the cooling of the planet, you need to develop a very good model for the thermal evolution. We have developed our own thermal evolution code and have tested against the solar system planets, and this is the source of our computation. One of the most important things that we need at studying if a planet could protect its life against harmful effects using its own magnetic field is knowing how the heat contained inside the planet could create a magnetic field. The creation of a magnetic field is a very complex magneto-hydrodynamical phenomenon. So it's very hard to do a particular model for each planet. So what we do and what any expert in this field do is using what are called scaling laws. Scaling laws are simple power law relationships connecting the amount of energy inside the planet with the intensity of the field. These scaling laws have been tested. They work properly for a huge range of physical conditions and a huge range of magnetic fields, even for low mass stars. So we need to rely that these scaling laws also will work on an extrasolar planet.
What's wrong with Saturn?
Okay, Saturn is a very special case because it actually has a very perfect magnetic field. Magnetic fields, as you know, are classified in two kinds. One is dipolar dominated magnetic fields, such as that of the Earth, very organized magnetic fields. Magnetic fields in this kind of planet works in the way that you can use a compass, and that if you go in the Earth, you can use a compass. But if you go, for example, to Mars and use a compass, the compass will point in very random directions in the surface of the planet. Okay, so real magnetic fields are a combination of these two kinds of magnetic fields. But you always expect that a dipolar dominated magnetic field has some multipolar components. In the case of Saturn, in a very strange way, it has a very strong dipolar magnetic field. So it seems that the magnetic field of Saturn is created with mechanisms very different than those that are assumed when deriving this kind of scaling laws. Okay, so that's why Saturn is here. We have two models of Saturn varying the dynamo parameters. Yes, this is the surface magnetic field in this planet. Okay, there is a very important point here, and this was our first contribution to this area, because it's almost a common-wise in planetary sciences right now that magnetic field intensity does not depend on the rotation rate. And it's very strange because intuitively you assume that if a planet is rotating very fast, it will create a very powerful magnetic field, but if the planet is rotating slowly, its magnetic field will be weak. Actually, there are not a strong dependence on the intensity of the magnetic field with the rotation rate. Actually, if you see in this quantity, rotation rate never appears. So, and this fact has explained a lot of things we have observed here in the solar system. But But what has been observed in labs and in numerical experiments is that actually there is an indirect dependence on rotation, on the rotation rate through what's called the dynamo regime. Dynamo regime is what defines if a magnetic field is dominated by its dipolar or very organized components or its multipolar components. What has been observed is that dynamos that rotate very fast have the same amount of magnetic energy that dynamos rotating very slow, but the energy is distributed differently. Dynamos that are rotating very fast has the most of its energy in the dipolar components, and dynamos that are rotating slowly have most of their energy, the same amount of energy, but in the multipolar components. So it's an indirect relationship that we have described mathematically very simply using a new scaling law, and that we can use at predicting the intensity, the field strength in planets that are extrasolar or other stars. Okay, as I said, Pablo will come back on this next week. The point is that using this indirect relationship between the rotational rate and the polar magnetic field intensity, we have been able to predict the intensity of the magnetic fields, the dipole moment of bodies ranging from Jupiter to Ganymede. So there is 7 orders of magnitude, not only in mass. Okay, mass is 4 orders of magnitude, but in dipole moment intensity. And all of this is due to including this dependence on the regime. So we are working with very robust, simple scaling laws to predict the intensity of the magnetic fields of very distinct type of objects. Okay, the other thing we need as an input is we need to know how the star interacts with the planetary magnetic field. The planetary magnetic field is not in a vacuum. Actually, as you know, we are inside the solar corona. The sun just ends at the heliopause or covers all the solar system. So actually, the magnetic field of the planets are inside the plasma, and in that plasma are magnetic fields from the sun. And the interaction among them creates a cavity that you can also know, which is called the magnetosphere. We can predict the properties of this magnetosphere if we know how the star is behaving, how large is the mass loss from the star, and how intense is the X-ray and ultraviolet flux from it. So using these inputs, we can model how a planet could be protected by its magnetic field. So for summary, in order to do this kind of work, we need an intelligent structure model, very robust. We have a very good models in the literature. A thermology model, okay, this is a newer development here. Dynamo scaling laws that are working in a wide range of planetary properties, and models for stellar SUV emission and mass loss, which are also more or less well known. Okay, so what we have obtained using this input about the constraints that the magnetic fields of super exomoons could face. So again, I want to leave this material for Pablo because okay, there are a lot of details inside here, but I want to to say you just a couple of words about this. What we have discovered, okay, with a couple of other authors recently, is that we live in a very special planet. Okay, the Earth has a mass which is not as arbitrary as we thought. Actually, if a planet has just two times the mass of the Earth, it starts to be really, really bad protected by its magnetic field. As planets starts to gain mass, as planets are more massive, the pressure and temperatures inside them creates a condition where the inner core, which should be solidified in the first gigayears, never solidifies. So actually, if you listen to about some planet that has been discovered with 4 Earth masses, you can almost for sure say that this planet has a pure liquid iron core. And in a pure liquid iron core, you will not have this latent heat feeding a strong dynamo. So actually, we have discovered this kind of critical mass above which dynamos are weaker and are also short-lived. The dynamo of the Earth has lived for 4.5 gigayears, 4.5 billion years. But for example, the dynamo of Venus probably died at the first gigayear. And some of the solar planets we are discovering have already extinct dynamos. But the dynamo of the Earth is already alive. Okay, there are a lot of very interesting things we have discovered about the dependency of magnetic properties of exo-Earths on its mass and on its composition. Although we'll talk about this next week. I can also telling you, for example, that we have also discovered, or we are also predicting, because as I told you at the beginning, this is a theoretical work. Since you are observational, I was concerned. This guy will ask for observations. Or where are your fluxes and your spectra? Okay, we don't have yet any observation. We don't have any aurora spectrum and radio wave emission from these magnetic fields. But we have a very good laboratory here in the solar system. So the solar system is our workbench. We have discovered, for example, we are predicting, for example, that very well-known super-Earths that are claiming to be habitable are actually, or have actually extinct dynamos. So actually these planets could be some kind of Venus analogs in their own stellar systems. If they are devoid of an atmosphere, of a magnetosphere, its atmosphere receives the flux of the stellar wind and can erode completely their atmosphere. Also, if you don't have an atmosphere, cosmic rays and high-energy particles coming from the star could sterilize the surface of the planet. So you can have a very beautiful and liquid water surface, but without life, because you have a lot of cosmic rays, and maybe you have extremophiles and some kind of blobs moving around, but resisting all these cosmic rays.
But not astronomers.
But not astronomers. Or if you don't have astronomers, nor telescopes over there. Okay, we have also several models of this. These kind of models have been developed in order to model how cosmic rays will hit the solar. And this, for example, the comparison between the magnetosphere of the Earth, as computed by our models, and the magnetosphere of this very famous planet. This planet this star was very famous recently because 2 additional habitable planets was discovered in the habitable zone of this star, and everyone was happy but not except us. We say, okay, they have discovered other rostered planets. Actually, they have discovered now. Right now, we are writing a paper with some colleagues from UK and Canada, trying to assess actually how habitable are the rest of the supposed habitable planets in this system. Okay, so this is a very important conclusion. Right now, we are in the middle of the seminar. There is an important conclusion here, and it's that not all that glitters is gold. Yes? Okay, not all planet that people say is habitable, because it's inside the habitable zone, is actually habitable. It's very important to understand that. And when you see this kind of table, this is a very famous table coming from a very popular site called the Planetary Habitability Laboratory in Puerto Rico. This kind of diagrams should be actually biased. To lack some information. For example, this planet should have a question mark here if you are thinking about magnetic constraints. Okay, so the summary of this part that will be seen very in depth by Paulo this week is that magnetic properties of exoearths depends strongly on planetary mass. This is very, very important. Low mass exoearths are like the Earth, our Earth. But massive exoearths probably are doomed in terms of magnetic protection. Rotation is very critical, and this is a very important point. Rotation is very critical. We have a very beautiful planet having a 44 hours period of rotation. And this could be long for some of you, and short for some of other of us, okay? But in extrasolar systems, could exist planets having a rotational period of 50 days, for example. Okay, one solar day is 50 days of us. In this kind of planets, actually they could have strong magnetic fields, but multipolar magnetic fields. Having multipolar magnetic fields could be something like this. No? Okay. Having a multipolar magnetic field will have an advantage. And the advantage is that you can see auroras almost everywhere in the planet. So you can be in the equator and see a beautiful aurora above you, because the magnetic field lines enters into the planet all around the surface. Only in the Earth or in planets having this strongly dipolar magnetic field, we will have auroras in two spots. Okay, we have with a very low statistics, we have concluded that probably 30% of the habitable planets, or the so-called habitable, or the claimed habitable planets, could be actually inhabitable because of magnetic field issues. But okay, this need a confirmation in the following 30 or 50 years. Sometimes for our students can wait. Okay. Yes, of course. Very interesting, because actually, for example, we have obtained that very massive terrestrial planets could have very strong dipole moments, because they have very strong, or they have a lot of internal heat able to produce this kind of. But these magnetic fields last for less time than in the case of Earth-like planets. Okay, so this is one point. And the other point is that it depends strongly on the rotational rate. For example, here, this planet is tightly locked. It means it has a very long rotational period. So its magnetic field, even being a very massive planet, could be comparable to that of an irregular planet. On the other hand, you have asked about how this magnetic protection works. The most important parameter here is this. It's called the standoff radius. The standoff radius is the distance from the center of the planet at which the stellar wind stops. It's stopped by the magnetic field of the planet. If this standoff, for example, here the standoff is measured in time in terms of the planetary radius. So if you have a standoff distance of one planetary radius, so the stellar wind will arrive even until your surface. Actually, okay, it's impossible because you will create a magnetosphere because of the shock. But for example, if you have a planet with just a standoff radius of just 2 planetary radii, the atmosphere is almost there. It's almost there. Okay, the atmosphere of the Earth is not until 100 kilometers, but actually it extends, forming what is called the plasma sphere, which is a very huge sphere of ionized atoms. And many of these atoms will be lost if they are outside, receiving the impact of the stellar wind. Also, at the beginning of the solar system, the increasing activity of the sun hits the atmosphere, and the atmosphere of the Earth could have been very huge at the beginning. And if you have a very small magnetic field, a very small magnetosphere, you will lose a lot of atmospheric content because of this shock.
I am surprised about that diagram because there is a discontinuity right at the point of the Earth. Physically, I would expect you to have some isolines, some parallel isolines, and then some point out there. Why do we have that strange discontinuity?
This will be an assignment for Pablo.
But
I can tell you that this is the discontinuity. This discontinuity is due to the formation of the solid inner core. When the solid inner core starts to grow, the magnetic field of the planet explodes. It starts to be very intense. Even, okay, this is very speculative since Juan Rafael was speculating there yesterday. I have we also speculate. But we are speculating that, for example, in the case of the Earth, the explosion of the magnetic field at 2.5 gigayears after the formation of the Earth coincides more or less with the diversity of photosynthetic organisms in the sea. So, okay, this is very speculative, but probably it could be some relationship between the development of the magnetic field and the development of life in the Earth. There are a lot, but a lot. You cannot believe how many beings in the world. You cannot imagine how much of them depends on magnetic field. A lot. It's not only Indians, it's not only whales, but actually there was discovered recently a bird that uses the magnetic field inside its eye in order to see where there are magnetotactic bacteria. There are plants grow faster in the presence of a magnetic field. Okay, so I want to close this parenthesis and continue just saying that this is the origin of the discontinuity. Okay, so yes, that's
surely the need for protection of the atmosphere must depend on the effective temperature and the solar activity of the whole star. Yeah. And since most known exoplanets are probably around stars or some dwarf stars, what
a very strong impact. Right. The small stars are very angry stars because they have these convective, are fully convective and produce relatively large magnetic fields. For example, this planet and this planet are around actually M dwarfs and are very close to their host star. This planet, for example, if I remember well, it's about the distance of Mercury from the Sun. But this is at the distance from Mercury to M dwarf. So as a consequence, the intensity of the stellar wind is very strong, and the intensity of the XUV radiation is also very strong. And this is also something that many people is overlooking. Okay, I know that, of course, these are very simple things to take into account, but actually people are just thinking about visible light and near ultraviolet light, which determine the condition to have water. But we cannot forget X-rays that hit the upper atmosphere, and extreme ultraviolet and stellar wind, which is also very important for this one. Do you remember our Avatar? Okay, Avatar is our last paper. It's about Avatar. Okay, Avatar is a moon around a giant planet. So this is another possible environment. Recently, it have been some development about the possibility to detect not only extrasolar planets but moons around those planets. Actually, right now there are some surveys to explore Kepler data in the search of exomoons, and apparently the sensitivity of this Kepler and the future tests is enough to detect Mars-sized moons around giant planets. So we are now concerned about, we are very concerned about the habitability of exomoons. So there have been studies about what makes an exomoon habitable, and now we are moving in that terrain, trying to see how is the magnetic environment of a moon. So we have in the solar system moons that are surrounded by a very complex and very interesting magnetic environment. For example, this diagram, which is mostly based on the measurement by Cassini, shows Saturn and Titan. Titan is actually inside, okay, part-time, inside the magnetosphere of Saturn. So the first thought we had about what is the magnetic environment of exomoon was, okay, exomoons will be protected by its host planet. They do not need intrinsic magnetic field. But, oh my God, it's more complex like that. Because of...
That's a painting, not a picture.
Yes, this is not a picture.
No. I mean,
yes, of course.
The scale
It's a model. It's a model. This is a magnetosphere model of the plasma inside it. This is people from JP. Okay, so what we have discovered is this. Okay, yes, Jupiter and Saturn have this huge magnetic field, so moons will be protected. Oh, but please stop, because if you take Saturn, which is at 10 AU, and put at the same distance than the Earth, the magnetosphere of Saturn will be compressed because of the plasma pressure coming from the solar wind. And the compression will be huge, actually huge. This is the radii of the standard radius, radius of Saturn when brought from the distance at which Saturn is now to the distance at which Earth is now. So let's compare. Titan is over here at this distance. This is measured in planetary radii. And this is the distance of Titan, and Titan is partially covered or partially shielded by the magnetic field of the planet, but partially unshielded. But if Saturn was at the distance of the Earth, actually Titan will be outside most of the time from the magnetic field of Saturn. And this will be very, very bad for Titan because Titan is tiny. It's actually tiny. Titan is of the size of Mars. So if Mars has lost its atmosphere because of the stellar wind, Titan will have lost also its atmosphere. So actually moons, exomoons seem to be also good. We have studied the same thing. It's very simple to calculate. This is part of the level of calculations. Because you just take the pressure of the stellar wind and put the magnetic field of the planets, and we have calculated this for different stellar masses, and the issue is also very, very bad in that system. There is a particularly terrible problem in the case of exomoon, because for planets you have a critical distance at which you will have an equilibrium in the surface, which is called the circumstellar habitable zone. But for moons, moons should be around planets in the circumstellar habitable zone. But moons also should be around the planet at a critical distance where not too much heat coming from tidal interaction is released from the inside. Actually, for example, in this diagram, if you are around Jupiter at a distance more or less of maybe 10 planetary radii, the amount of energy, the moon having this eccentricity will be tidally heated at a level where you will have so much a large temperature in the surface, and you will not have water. So the problem is that the moons have an extra sources of energy if are around giant planets. Here we have calculated how the standard distance evolves as the stellar activity recedes. This is the standard distance of the planet, of a giant planet, of a Jupiter-like giant planet located at the habitable zone of a 0.7 star. This here is the inner edge where too much tidal heat is released. So the point here is that during almost 3.4 gigayears, the standard distance is below the minimum distance at which you can have an habitable extrasolar moon. So actually to have a moon habitable, they should be here. But the standard distance of the planet is inside for almost 3 gigayears. So the point here is that probably most of the moons we have trying to calculate, this is a very complex plot, it's a lot of information, but we have calculated that a lot of moons in the universe should be actually unshielded by the magnetic fields of their own planet, of their host planets. As a result, this dream to be protected by your father is actually just a dream. So, what could we do? Actually, it's very hard. We are computing right now how several candidates right now are behaving, and we are discovering that these planets, these candidates, habitable planet, giant planet candidates that could have exomoons are really bad at having habitable or at least shielded exomoons. So, but what happens if the moon is actually inside the magnetosphere of the planet? Okay, if you are inside the magnetosphere, you are good. No, it's terrible. Terrible, because, for example, I don't know if you know that Jupiter is a particle accelerator. Actually, Jupiter, having this huge magnetic field, takes cosmic rays, very high energy cosmic rays, and captures them. And if you are inside the magnetosphere of Jupiter, okay, you will receive an enhanced flux of high energy particles. In the surface of Europe, for example, if you stand up in the surface of Europe, you will receive in a minute, in just 1 minute, 500 chest X-ray, the equivalent of 500 X-ray, how do you say? X-ray pictures. Okay, so radiographies. So, being inside is not actually not good because you are inside of particles. Okay, but there are regions over here where Titan is. Titan is a very good place. It has an atmosphere. Probably it will have liquid water in the future, and probably it will have developed life. But actually, at the distance of Titan, which is in the skirts of the magnetosphere, there are planetary wind. Actually, the magnetic field of the planet drags the plasma inside the magnetosphere and creates a wind almost as intense as the stellar wind. For Titan, it has been computed that in the last 4 gigayears, it has lost more or less 20% of its atmosphere, 10% when it's outside, and 10% when it's inside. So there are no good news for exomoons. And maybe if you listen about Avatar, this Avatar thing, you could think about it. Okay? For example, in the movie, you see this huge planet in the sky. It's very romantic, very romantic. No, if you are so close to the planet, so close to the planet, probably the moon will be volcanic, as you know. So it's not good to be at that distance. You should see the planet very far, but if it's too far, you are outside, and probably you don't have atmosphere. So, okay, just science. Okay, the summary, for example, is the magnetic environment is much more complex. That magnetic field to provide most of the magnetic protection, but the magnetosphere of these planets are cheap if they are closer to this star, and also inside this magnetosphere you will feel very different effects that affect habitat. And last but not least, we have discovered recently with some colleagues from the US that there is hope, because if you see, habitability should be considered a more complex thing for super Earths and for exomoons. But there is probably a hope. There is a place in the universe where all these things that I have been describing today could be very different. And this place are closed binaries. Closed binaries. You know that we have discovered recently, maybe the last 3 or 5 years, okay, very recently, maybe 2 years, we have discovered at least 6 closed binaries. When I talk about closed binaries, I mean binaries being at a distance below 1 AU. Okay, you know, 2 stars being closer than, for example, Mercury to the Sun, or Venus to the Sun. We have discovered planets orbiting this kind of binaries. It's very hard to think, how can a planet orbit 2 bodies instead of 1? But these systems are stable and works. So these closed binaries have an effect which we have hypothesized and we need to confirm, but it seems solid, and it's that because of tidal interaction among the stars that always start their lives rotating very fast, because they capture most of the angular momentum from the clouds. Maybe some angular momentum is pushed away into the disk, but some angular momentum rests into the star. So the stars start their lives rotating probably at periods of rotating around 5 days, 10 days. The sun, for example, at the beginning was rotating at 7 days. If there was rotating today, is 27 days. But what happened? If a star is rotating very fast, So the magnetic fields will be strongly dipolar. So the corona of this star will be will be huge, and probably the intensity of the magnetic fields in the surface will be also huge, and there will be a strong emission of high energy radiation. But what happened in a closed binary? In a closed binary, the tidal interaction between the binaries, among the binaries, probably during formation, or probably after the formation of the system, will break the stars. So these stars, even being just born, even being too very young, if they, for example, have a period of 20 days in the orbit of these stars, due to this tidal interaction, they will be rotating also at 20 days. So, for example, a solar mass star in a closed binary, having just, for example, 500 megayears, which is very short for Alpha, will have an apparent age in terms of magnetic activity of 3.5 gigayears. So in a star with this condition, with this activity, the mass loss will be less, the XUV radiation will be less, and probably Venus could have withstood could have been able to withstand this condition. So probably if we have two stars instead of one, we could have life in Venus. This is our... Okay, we are finishing. And we have studied systematically this effect for the already known Kepler binaries, and we have discovered that several of them are especially well suited for this kind of effect. You will hear about or listen about this Kepler 34 in the future, because I think we think that these binary have multiple habitable planets. Okay, maybe it will take a lot to discover these planets, but I think that actually there are several habitable planets inside this region. So the point here is that around Kepler 34, probably inside the habitable zone of this binary, the XUV radiation and the stellar wind is weak, is very weak. So planets, even having very weak magnetic fields, could have been withstand this condition and be habitable today. Also, okay, this is for the XUV radiation, the level of XUV radiation, which is very low, very low. This is 1/5 of what we have seen in the solar system. And also for the standard distance. The standard distance of Venus is something 3.8 at the beginning of the solar system. And as you see here, a Venus-like planet could have standard distance much more larger. We are looking, our search right now is trying to quantify. This is an ongoing search. Trying to quantify how many binary stars are in the galaxy having these special enhanced habitability conditions. And this is what we are doing right now, some statistics. We know that binaries are frequent in the galaxy. Actually, the fraction of the stars, this binarity, the fraction of the stars having a companion depends on the mass of the star. This we know normally we know this 60%, but actually for solar mass stars, the most recent, this is a 2012 paper. Actually, for the solar line stars, the binarity fraction is 50%. So half of the stars with the same mass of the sun in the galaxy could be in binary system. So this could be very good for us. Well, actually, there are some problems. One is the problem we were discussing yesterday, and is that in the galaxy there are a lot of stars having very low mass. Actually, having a solar mass is not as common as having 0.2 or 0.3. So actually, this could be advantageous but in the galaxy, the most stars are actually there are 30% of the stars in the galaxy. The most of the stars in the galaxy are invariant. There is another problem, and is that the distance among the components in the binary are distributed in this way, and if you remember, we are looking for stars or binaries having 10 days of orbital period. So we are looking for a star here. But most of the stars have periods of the order, for example, or the order of 10 years. So actually, we are working with, we are looking for 5%, more or less 5% of the galaxy, of the stars in the galaxy. And in this 5%, it's not important, you are looking for these stars that are in the right region. We are looking for stars in this band. But this point is good. This is the observation corrected by, for completeness, the distribution of periods and eccentricities for closed binaries. And what we have seen is that in the case of closed binary, and probably for chance, for chance, there is a process here. The peak and the distribution, for example, in eccentricities, and the peak of distribution in binary periods are particularly conducive to this very good region here, where habitability is somehow enhanced. So right now we are trying to generate a synthetic population. We are trying to recover, for example, 100,000 of the stars in the galaxy disk, and trying to evaluate one by one. Okay, these are random stars. One by one, how are habitability inside this around this star constrained by magnetic fields. Our goal is trying to compute how many stars in the galaxy are probably enjoying this kind of enhanced habitability condition. So, as I told you, this is a work in progress. Probably we will discover, our estimation is that probably 1% of the total number of the stars in the galaxy are in this kind of system. This is a small number. But if you take 100 billion, this is a billion of planets or systems in the galaxy where you have 3 planets, 3 habitable planets instead of 1. So this will be very interesting place in the galaxy. Okay, so vertical synchronization, enhanced habitability. Solar mass twins are the best fitted. So if you discover double star, okay, these are spectroscopic binaries that are solar twins, maybe you are looking at the right place. Low mass stars that are very active at the beginning of their lives are actually good if they are with a solar mass star, because the solar mass star put the planets farther away, where the mass loss from the low mass stars is less. And we have estimated until now that the fraction of the stars in the galaxy having this is 1%. So, thank you very much. Yes.
Para preguntas. La primera es, ¿cómo... ¿Cómo afecta la habitabilidad de las lunas el hecho de que los planetas inviertan, digamos, la polaridad del campo magnético? Es decir, habría periodos en el cual la luna no es habitable y qué tan fuerte es el impacto. Segunda pregunta, en los sistemas binarios, tienes un planeta, entonces la pregunta es, ¿de qué orden de magnitud es la interacción de marea que puede hacer que el planeta sea inhabitable justamente por el calentamiento interior?
Okay, the first question is about the inversion of the magnetic field in giant planets.
Yeah.
Don't worry about it. In giant planets have very strongly polar
Multipolar planets, for example. Multipolar magnetic field.
Yes, for example, Uranus and Neptune has multipolar magnetic field, but for that case, inversion doesn't matter because they are multipolar. So inversions are important if you have, as in the Earth, a critical magnetic field in the boundary among them. So magnetic field of the Earth, yes, jump in between these two states, but in the case of giant planets, we will not have this case. Even it's easier for a star like the Sun. And the second question was about the tidal heating.
Yeah.
How large is the tidal heating? Okay, just think about this.
This since I don't know, there is a range of
Distances, yes.
Well,
Yes. Think about it. About this. From the interior of the Earth are coming out 4 milliwatts per square meter per square meter. This is the heat that is released by the interior of the Earth. In Io are coming 2 watts. So it's almost 1,000 times more heat coming from this planet. So actually the distance, the critical distance is large, is relatively large. In the case of Io is inside this distance, but for example Europa not. Europa is farther away. So the distance is more or less 10 planetary radii, and it depends on the eccentricity of the orbit of the.
I think Mario was talking about binary systems.
binary system.
So
Binary system. Yeah,
binary system.
you have
you mean binary systems in the tidal effect of binary
In the
in
planet.
the planet?
Yeah.
Okay. Oh, this is also very interesting because actually if a planet is around a binary system, its rotation period doesn't get locked to its orbital period, but to the orbital period of the binary. So it's very interesting because if the binary has 20 days, so and the planet is even at 10 days,
okay.
so it will be locked.
All the time the same configuration.
Yes, from the start, and this is very good for science fiction. We can break from a planet very close by to a binary system. You will see the stars always in the same configuration.
Yeah.
You will not see the stars doing this if the planet is tidally locked. But of course, there will be some heat released by this tidal interaction. But you have to take into account that the tidal heat just happens at the beginning of the process when the planet is locking. So it could take 10 million years.
So we are assuming that
If
the
orbit
stars and the planet are in a Lagrange configuration.
Oh,
But that happens for close planets.
Yeah.
But in the case of binary systems, the habitable zone of the binary system is
far away.
far away. So this kind of planets there will be
tidally.
low. So
Another advantage.
probably not.
I'm really here the devil's advocate. Okay, so the question for years, the magnetic field of the Earth has shifted
Yes.
many times in the past, okay? Every 1,000 years or etc. So how do you explain that we still have life on Earth?
Very good. That's because the time during which the planet is devoid, or the magnetic field of the planet is very short in terms of the time scale for atmospheric black holes. So actually, it's true that during these inversions, the magnetosphere of the Earth shrinks, but it blows up again in a time scale that is not too bad for the atmosphere. But in the case of protection against cosmic rays and higher particles from the sun, the answer is more or less the same. But we also have to take into account that the magnetic field doesn't disappear completely but actually the Earth is left with a multipolar magnetic field that still protect you a little. But there are, okay, another parenthesis, another speculation, there are some biologists, there are some paleontologists looking for evidences of ecological disasters during inversions. And okay, there are some ideas, but probably it's not too important for life.
And another thing, when this inversions happens, the main thing is that the dipolar moment increases, but at the same time the multipolar
Stay there.
so there's some kind of equilibrium of the.
Aurora will be beautiful.
Yeah, but of course the magnetosphere is very strange.
I was wondering about the time scales of planetary formation. So obviously you have to form the planets before the star gets rid of all the dust in the disk. How is this in those binary systems?
Yes, this is one of the most important concerns here, because there are, as in the Star Wars and things like that, there are authors that say that you will not ever have a terrestrial planet in this kind of system because of this dramatic and very dynamic environment. And there are people saying that oh, it's possible, it's possible. So, yes, the time scale for our terrestrial planet, for the formation of terrestrial planets is 10 megayears. 10 megayears. So, you expect that, okay, some authors expect that during these 10 megayears, some part of this remains there, and some part of the planets that are still there, and you can go. But the range, the error bar is huge. But this was one of the concerns. For example, the referee of this paper arose during the review process. So you are criminal about this, but you have first ensure that you have planets around these planets. Okay, we have some evidence that we have giant planets, but the authors that said that it's not possible to form say that these planets fall very far away, then migrate to the inside. Because they are giant planets. But we also suspect that. Yes, for rocky planets happen, but probably we will have also this kind of type 2 migration in space. Yes?
I'm a little bit concerned about this, the last part you showed.
Yes.
The modeling of this population of binary.
It's calculated.
It wasn't completely clear for me. How do you model the population of binary stars?
Actually, yes, it's tricky in the statistical terms, because to generate the properties, you have 5 properties: the mass of the main star, the probability that it's an binary,
yeah. How is the probability?
Yes.
Even I guess. Who do you constrain the probability for a star to be part of a binary with the property you want?
Do you have a marker? Okay, maybe I can explain it in the air. So the probability is very complex. Actually, what people, for example, I don't know if this is light, these people working with the dynamics of stellar clusters, what they do is that they put stars in a cluster, in a very dense cluster, put some masses from the IMN, and then leave the cluster until it gets relaxed. And at the end, they look for the properties of the binary actually form there. What we are doing is taking the statistical properties that have been observed in the stars in the galactic disk and trying to create a huge probability density function depending on the mass of the main star, the binarity fraction, Q, the period of the star, and E. And then this is a very complex 5-dimensional function, and you need to generate all these properties using some kind of rejection in 5-dimensional, probably metropolis method. But we have the luck that you can decompose this thing in using the chain rule of probabilities, using these conditional probabilities, and at the end, the only thing you have is something like this, like the probability that a star being a binary having this, having this and this, the probability that you have this binarity, the probability that you have this, having this, the probability that you have this and this, having this, and then the probability that you have this. So using probability, you can decompose this huge probability in these terms and work with each of these probabilities to generate your synthetic population.
This will actually give you an overestimate of the fraction, because you're not including the process associated with the physics of the formation of the CoLO. The placement of material, because you're assuming the stars are forming together, so you are not taking into account the process of the formation in. So you are not taking into account the heating of the material, which somehow will affect, for example, the formation.
You mean for the protoplanetary disk? Yes. We are
so
not
that's going to give you like another estimate of the fraction of the stars you will have.
Yes. What we are trying to compute is not the amount of planets, because it's very hard. It's like Drake equation or something. But the amount of habitable niches. These habitable zones are very good, very well suited for having planets. And leaving some other astrophysicists to solve the problem of planetary formation in binary systems. Yes. So yes, you're right.
And this probability is after formation, just the probability belongs to one of these special binary systems.
Of being there,
yeah.
So does your research mean that we should keep the concept of habitable zone only for binary systems and get rid of it for, I mean, given the fact that you say that it will depend on the magnetic properties of each planet, whether or not it will have life or conditions for life, does that mean that habitable zone is a useless term?
Okay, I have some philosophical opinions about that, but according to our research, no. Habitable zones in the galaxy, every star in the galaxy has an habitable zone, are probably very populated of terrestrial planets, but in the case of M dwarfs, we think that magnetic fields are not enough to protect the stars. So we can start maybe thinking more of the case of M dwarfs. But you live with a lot of solar mass stars having these habitable zones. The point is, and the difference, what our research is showing, is that in this habitable zone are around single solar-like stars. You could have probably one, probably two planets inhabited, or probably one, probably two planets, habitable planets. But if you are around solar twins, probably you have 3 planets, 4 planets. So, if you want, you know that all this research about habitable planets in the universe is just to direct the future research. So, if you want advice to look for habitable planets, maybe the advice is don't look just in solar-like stars, but look at binary. Look at if you find some binary, look very well, because probably you will have the 3 planets having no sun, having methane. So this is the message of this. Yes.
What if we have 2 planets as big as planets as big as Jupiter and Saturn, for example, each one with their magnetic fields, and perhaps an intermediate exomoon is passing by or something, where the magnetic fields act on on an analog way to binary stars, to binary stars with their magnetic fields.
So you mean having an exomoon in a binary star?
An exomoon in between two planets.
In between two planets.
I'm not picturing two planets and an exomoon.
A single planet.
That
Yes.
way, I'm figuring out, for example, imagine Saturn, right?
Yes.
And Titan.
Yes.
If Jupiter, if they were
Yes.
a little bit closer to Earth, right? I mean to the Sun, where where Titan would be on the habitable zone, and Jupiter and Saturn were closer together, so that the magnetic fields
We're zooming up.
were analog to your model on binaries.
Okay, no, but in this case, okay, the probability of having this configuration is very low because of the dynamical issues. Because if you have Jupiter and Saturn very close by, on the other hand, if they are in different orbits, their periods will be very different. So they will just join or be close during one time each orbit. So maybe this moon will be the tail, the magnetic tail of the other planet. Actually Saturn.
Something like that just happened with Saturn and
Yes, but this is very bad because actually Jupiter acts like a lens, and it directs the stellar wind through its tail. So it's not good being the tail of Jupiter. But no, having both two planets is very unlikely. Mario.
Yes. You find the conditions for isolated stars like the Sun for a special region for habitable planets, but you extend to the binary, it's a better situation for that conditions. What happens if you have 3 or more stars?
That's a very important thing we are trying to assess also. And in that case, the problem is that multiple systems in the galaxy are actually hierarchical. So actually, it's not easy to find 3 stars being in this kind of special dynamical situations where they. So what you have actually is a close binary and a third star, like in the case of Alpha Centauri, where you have 2 binaries very close by and a third one. In that case, what you have is actually a circumbinary system here and a normal, almost single star system here. Of course, there will be an issue. Being in the habitable zone of this third star will be interesting because you will receive some light from the binaries very far. But actually, what I guess is that, and what we will do in our statistical search is treating this star as a single star. Okay. Thank you. David.
Couple of questions.
It is not our supersymmetry, because supersymmetry is
I don't like it. The first one is, can the tidal heating on an exomoon induce a magnetic field in the exomoon?
Yes, very good question, because actually, for example, if a moon have a liquid water mantle, like Europa, and this mantle of water is sustained by the tidal heat. Since water is also a conductive liquid, you could have there a dynamo action. So actually, it's very possible that a moon having this kind of condition will have a magnetic field, but in that case, you will, anyway, you will be too close to the planet and will receive all these particles, high-energy particles trapped in the magnetosphere.
And if the magnetic field of the moon works like a shield for the moon in the magnetic field of
This is the case of Ganymede. Ganymede is inside the magnetic field of Jupiter and have an intrinsic magnetic field, very hard to measure because when water fly by, you measure something, but okay, but the point there, okay, we will have the same constraints that we have found for super Earths, because the moon should have a strong enough magnetic field to be protected against the the radiation belt particles and against the plasma wind inside the magnetosphere. So you will come back again to the condition for super Earths.
And the second one.
There are two.
In the slide of the summary for
exo-Earths, yes,
exo-Earths, you have a statement that
yes,
in which you say that 1, 3, blah blah.
yes. One out of 3. Yes.
What is the confidence level?
This is pretty irresponsible. This is a statistics made of 3 cases, so it's very hard to be confident. But you know, statistics like that. You just no. 95% is 4. Oh, you should have. Yes, of course. Your class today was cancelled. See you at 4 o'clock.